All right, so we're almost done with chapter three. And there's really just this one topic left to cover. And really, this is just an introduction to the topic. Chapter four is all about what we're about to do. This is basically like a coming attraction of what we're going to be doing in chapter four. So we want to take a look at this right now. So when this is done, I also have or will be posting a set of problems for chapter three so that we can have more practice, which I think everybody wants to have more practice. The great thing about calculus is that more practice is always better. So it's about 12 or 14 questions that are taken from chapter three. And so I'll be going over with you with the next session, and that way you'll get a little bit more practice for when you're working on your assignments. Okay. Now, also, I think that the first test will be based on everything we've done up to chapter three. So, in other words, um, chapter four, which will be starting pretty soon, will be not on the first midterm. Okay. So, I'm still putting together the test. I'll let you know when it's ready. But right now, we're going to finish up chapter three. These are the slides 3D. And then when we're done here, the next session, I'll go over the problem set, and then you'll be completely ready for the assignments. And then we probably should have a little bit of reviewing for the midterm anyway, so we'll do that as well. But right now, I just want to go through the antiderivatives, as they're called. And the idea here is that this is the reverse process of taking a derivative. Um, it's usually often though, you see the word antiderivative here, it reminds us that this is the reverse process of taking a derivative, but usually we hear it referred to as integration or taking an integral. That's the more common name that we give to this process, but they both mean the same thing. So the antiderivative of a function is a function whose derivative is f of x. Okay, so the notation that we'll be using here, by the way, is this. Lower f of x, you've seen this a million times, is a function. F prime of x is the derivative of it, the function. So now we're going to introduce capital F. And this is the antiderivative or integral of f of x. Okay, and so we can prove that this is actually the correct function. If you see directly below, f prime of x means we're taking the antiderivative, and if we now take its derivative, it should return us to the original function. And that's how we would know that we've done this correctly. So in other words, when you solve for the antiderivative, capital F of x, you can double check it by taking its derivative and making sure that it is equal to the original function f of x. Now, of course, this only applies in the domain of f of x. So in other words, if there's any sections or parts of the real number line that are missing from the domain, then they would not apply to this antiderivative either. So anyway, here's an example right here. F of x is 2x. Now, you haven't seen y, but I'm going to tell you right now, the antiderivative or integral is x squared. Okay. We'll learn how to do this very quickly. But then what you can see here is if that's the case, then the derivative based on the power rule, or how that works, if f of x is k x to the n, and then f prime of x is nk x to the n minus 1. So here in this case, k is 1, n is 2. So that f prime of x would be, capital F prime of x, I should say, is nk x to the n minus 1, which leaves us with 2 times 1 times x to the 2 minus 1, which is 2x. So because the derivative of this capital F of x does return us to the original function, we can say that this must be derivative or integral of 2x. Okay, now here's the big question. How did we get that result? Well, by the way, before we continue any further, I did go into the book and I found the table where all these integral functions are. It's section B at the end, integration tables. Oh, and it's a big one. I know, by the way, many of these you'll never see. I mean, there's some very there are a lot of cases in here that we'll never quite get to in this course. Maybe in Calc 2 or 3 you'll run into these. For example, these are the hyperbolic trig functions. But some of these you'll definitely run into like log u and that type of thing. So in other words, the chart on the arc sines and arc cosines and all the rest. The charts are here just as a memory aid. For example, the integral of sine u du is negative cosine u plus c. We'll probably use that fairly regularly. Some of these other ones, not so much, but you can see there's a lot of them. There's a lot of cases we may encounter with integration. So in general, I think that people find that integration is more difficult than taking derivatives, but we have to be able to do both. And so, and by the way, oh, and this symbol here, we'll get to that too. That symbol tells us that we're taking an integral. Okay, we'll be introduced to that very quickly. All right, anyway, now here's one of the strange things about integration. We just got through showing here that f of x equals lowercase f of x, that is, 2x. And we showed that capital F of x, the antiderivative is x squared. And we know that that's true because f prime of x is 2x. But we could also make the case this is also the antiderivative or integral of f of x, because if you take the derivative here, again, based on the power rule, we'll have 2x. The derivative of this plus 1 is just 0. Well, now that opens up the floodgates, because now you can make the case that x squared plus 2 is also the antiderivative of x. And in general, we can make the case that x squared plus any constant c is the antiderivative of f of x. So this is the general form, the antiderivative of this original function. So in other words, the antiderivative is actually a collection of functions. Every one of them, which one differentiated will bring us back to the original function. So we have to get into the habit of whenever we take an antiderivative, we have to add that c at the end, because you never know which constant will be the actual one, including 0. That brings us back to the original function. So in other words, any one of these is a potential antiderivative. So what we'll be doing is expressing our result as x squared plus c to indicate that any c would work in this case. So that's something that's going to take some getting used to. Okay, so that means it'll be x squared plus c. Whatever you get after you follow the rules for taking antiderivatives, you'll always add that c at the end. Now, here's another similar case. We're told that the original function is 3x squared. And so it turns out that x cubed, if we take its derivative, using the power rule, we get 3x squared. And again, we didn't really learn a technique yet. We just want to note that That being the case, it must be true that the antiderivative is that x cubed plus, of course, this constant. Because using the power rule, f prime of x is clearly just 3x squared because the constant has a derivative of 0. So the question again is, how did we find this? Well, I mean, maybe you noticed it or you thought of it very quickly, but there are techniques that we'll learn to help us do this very quickly and easily. We're not going to keep saying, well, if I think about it for a minute, no, there's a specific set of techniques that we're going to be learning. Now look at this one. What is the antiderivative of 1 over x? So you remember the derivative of log of x is 1 over x, which implies if this is our function, the antiderivative is log x plus c, because if you take this derivative, you'll get 1 over x. Okay? All right. Now for this one, remember, we have to be careful because the domain of log x is this. Okay. The log of x is undefined. For 0, it is an asymptote to the function. And then from then on, it just continues to increase as x goes to infinity. And so that means that the antiderivative is going to be different if we have a negative x. Okay, in other words, you can define it, the antiderivative for negative values, but you're going to end up with something a little different. Okay, well, actually, in this case, it's the same thing, but so we have to be careful to keep an eye on the domain when we take integrals or antiderivatives. Okay, so what this is saying then, and by the way, how can you tell? Because if you say that the antiderivative is log negative x plus c, the derivative does work out correctly. So what this is implying is that the antiderivative is log x when x is strictly positive, log negative x when x is negative. So what we often see instead of this, because this is kind of an awkward way of writing it, is that we end up with the antiderivative is simply log of absolute x plus c. Okay. And all that means is it's the same thing as what you're seeing here. Okay. So of course you notice that x can't be 0. And so this is how we're going to express for this one case, we need that absolute value. Okay. If you look at this chart, you'll see that this pops up every so often. There are absolute values. Whenever you see logs, there's often absolute values involved. And then we can do the same thing for trig functions. So what is, if the original function is f of x equals cosine of x? Well, we recall that the derivative of sine of x is cosine of x, which implies, again, that the antiderivative must be this sine x plus c. By the way, this one is in our table. Like if you're working on a problem like this and you say, I don't remember this one. Yeah, so in other words, the integral of cosine, now here it's got a u. U means it's a function of x. It means whatever it is, this is how we write our answer. So the cosine, integral of cosine, which again, you're using this symbol to indicate that you're actually taking an integral, which we'll see in chapter 4. It means that when you take the integral, you'll end up with a sine of that same u plus c. Okay, we'll introduce that symbol in chapter 4. E to the x. Now remember, if this is one of the simpler ones because we know that the derivative of e to the x is just e to the x, which means in this case, the function is equal to its own antiderivative, except for that c. Okay, so end up with e to the x plus c. Oh, here it is. We do introduce it here. So we're going to call these integrals. So the symbol is this. Now, this symbol is an interesting symbol. The point of this symbol, supposedly, is that if you remember from your travels, this is the summation operator. But this thing is usually normally used to represent, well, I shouldn't say that it often is used to represent finite sums, although it could be used to illustrate an infinite sum. The integral symbol is written like this to indicate this actually represents an infinite sum. Now you may not be able to visualize that just yet. When we formally define integration, you'll see what this is all about. It's actually we're using geometry to formally define integration. And so what you actually end up with is an infinite set of rectangles whose area equals our integral. So that's where this notation is coming from. So to integrate our original function, and it's written with this dx, and again, you'll see why when we formally introduce this idea in chapter 4. What you're seeing here are the areas of an infinite number of rectangles, and that brings us to the antiderivative or integral f of x plus c. Now, if you notice, we're not going to end up with a specific constant for our result. So this type of integral is referred to as an indefinite integral because it will not be evaluated at any particular value of x. If that's what we want, then we'll use what's called a definite integral, which again, we'll see this in chapter 4. Is defined for specific values of x. And therefore, the result is a constant. Okay, not a function like this one, but a constant like 3 or 10 or something like that. Now, we're going to start to introduce some of the basic rules. So we have a power rule. For the differentiation, we have a power rule. Our old friend, the power rule for differentiation, if we have this, then f prime of x is nkx to the n minus 1. For integrals or antiderivatives, the integral of x to the n power equals x to the n plus 1 power over n plus 1 plus c. So you notice the difference with when we're differentiating, we're subtracting 1 from the exponent. Here we're adding. Don't forget the c. And of course, we can't do this if n is equal to -1. We have to try something different. But for any other real number, this is our power rule. Okay, so for example, what if I'm trying to find the integral of x to the 4th power? Based on that power rule, let me copy it here so we can see it again. In this case, n is 4. So therefore, n plus 1 must be 5. And down here, same thing. And we have x to the 5th over 5 plus c. Now, although it wasn't done here in the slides, why don't we prove this? So the original function, remember, was x to the 4th. We're claiming that the antiderivative or integral is x to the 5th over 5 plus c. So what is the derivative of this function? Well, this is the power rule for derivatives. what we can probably do is write it like this. It might be a little quicker. 1/5. Now here we can apply the power rule as 5 times x to the 4 minus 1. This goes to 0. We won't have to worry about it. So what did I do? I did something wrong here. This is supposed to be n minus 1. Sorry. There we go. So it's x. These cancel out to the 4th. So in other words, although it wasn't absolutely necessary to do this, it's nice to know that once we find our integral, we can double check to make sure we did it correctly by taking its derivative using whatever technique we need and bringing ourselves back to the original function. So in other words, what we're hoping to find is that f prime of x, capital F prime of x, equals the original function. And that means that we've done this correctly. All right, now how about this one? Again, I'll copy the rule so you start to get used to it. So our exponent is -2. -2 plus 1 is -1. So we have x to the -1 over -1. And of course, x to the -1 is the same thing as 1 over x. So we can rewrite this very simply as -1 over x plus c. And if we choose to do so, we can double check this with the power rule and make sure that it brings us back to our original function. F of x is x to the -2 power. Okay, so the antiderivative or integral is this. Okay. Now, it turns out that if we have the integral of a constant, k is the constant, we just end up with kx plus c. And again, you can prove this by applying the power rule. So if I want to know the derivative of kx plus c, so here I've got a times 1x to the 1 minus 1 plus 0, k x to the 0 equals k. Okay, so it works. Okay, so we'll see this all the time. All right. This one in particular, we'll be using this one constantly, as we will be using this one. So here, for example, the integral of 3 dx is very simply 3x plus c. Also, by the way, I want to point out you can factor constants out of the integral sign. Also, we haven't gotten to that point yet, but the integral of dx is just x. Okay, keep that in mind when you're doing these. If you just have the integral of dx by itself, that gives us back x. Oh, well, there it is. I just made my own point here. So here with this one, we move the 4 outside. And now we apply the power rule for integrals. So that x to the 5th becomes x to the 6th over 6. We still have this 4 out here, plus the constant, of course. We end up with 4x to the 6 to the 6th, which is the same thing as 2/3 x to the 6th plus c. And again, you can feel free to double check this with the power rule. Now, that's fine as far as it goes. So far, we've been considering only constants and powers of x. What about logarithmic and exponential functions? Well, it turns out they're relatively straightforward. And here they are. The integral of 1 over x dx is, as we saw earlier, log absolute value of x because it's negative when x is positive, positive when x, Negative when x is negative, positive when x is positive. So we leave it here as the absolute value. Down here, the integral of e to the x dx is very simply e to the x plus c. And sometimes, by the way, notation-wise, this expression is often written like this. It, of course, means the same thing. Well, let's try this one. Now, the 4 can be moved outside. So the 4, now here you can clearly see this is what we're going to get here, log absolute value of x. Don't forget the 4. And so this one is very simply 4 log absolute value of x plus c. Don't forget the c. Now, sometimes, our job with these integrals is to clean them up a little or rearrange them algebraically to see what technique we should be using. Here, that's very straightforward because we're just moving a constant outside the integral sign. But for others, you'll see it's going to get a little bit messier. And this one too, same thing. We've got, if you move the 5 outside, here we go. Here, this is what we saw earlier. The integral of e to the x dx is simply e to the x plus c. And so that leaves us with 5e to the x plus c. Wow. So those aren't too bad. Now, there's a handful of trig integrals that are not too painful. We'll start with these. And you did see them. And here, remember, now here, this is u, which is a function of x. It could be literally anything, but we're going to start with just x itself. So the integral of sine x dx is the negative cosine of x plus c. And the integral of cosine x dx is the sine of x plus c. Now, again, the reason behind this is because f prime of x in this case, if you remember, that gives me negative sine x. And then we also saw that. And so if I do the same thing here, capital F prime of x is the cosine of x. And this, of course, the c's always drop out. And that's how we know that these are correct. After a while, you'll have these practically memorized, but it's nice to know that you can go back and double check and make sure these are actually correct. Now, these are where it gets a little messy. With these, to demonstrate these, we end up needing to use a lot of trig identities. There's a lot of trig identities that we can choose from. For now, we just want to go through these and recognize them when we see them again. The integral of secant squared x dx is tan x. Here, this one is negative cosecant x, and the last one is simply secant x. And again, these are they're probably in here. They sometimes, there's so many of these. But if you look hard enough, you'll find these eventually in this chart. Yeah, they've got so many to choose from here. Now here's an interesting result. You remember the sum rule with derivatives. If you have something like this, so something similar is happening here. We can break up this expression into the sum of two different integrals. Okay, so why are we doing it? Well, sometimes it makes it easier to see what rules we should be using. Rather than having one huge messy expression, we can break it up into simpler expressions and evaluate them individually. Okay, So that's what we're going to do here. Now, this one is going to ask us to use the power rule. And don't forget, x is the same thing as x to the first power. So we're using the power rule, the first term. Just sneak that in there. And then, of course, the second one, we saw a couple of slides ago that the integral of e to the x dx is very simply e to the x plus c. Now, by the way, here's an interesting twist here. The first one is going to be x squared over 2 plus c. And the second one will be e to the x plus c. The thing is, we don't know. Technically, you should write this as C1 and C2 because they're may not be equal to each other. But because we don't know what the constants are, we can just simply combine them all together into a new constant. And so we will write this as x squared over 2 plus e to the x plus c. Because again, we don't know what the actual values are. All we know is that it's a sum of some kind. And so we can just leave it like this. Right. So we just lumped them together. Now, by the way, if we were given more information, we could figure out what the C is. But as things stand right now, we don't know enough to solve for it. You would have to know like initial values, things like that. It's, it can be done, but not just yet. We're not going to get that done just now. All right. So, so yeah, and of course the same thing applies to subtraction. And then, of course, down here, we've already seen this, the k, the constant, can be factored out of the integral sign. So these are pretty straightforward results. And if you notice, this, of course, is the antiderivative or integral of f of x. It's g of x because it's a capital. Remember, we're using the capitals for integrals. And then here, it's the same thing. We have k times f of x plus c. So that's the most general possible expression of these results. Now, look at this one. It's a polynomial, so we can break it up into 4 separate integrals. And we're actually not done yet. If you notice, there's a lot of constants floating around here. We're going to actually take them outside of the integral sign just to make things a little simpler. But notice that, just like before, we're taking the terms, adding this one, subtracting this one, adding this one, and now we can do some simplification. We move the constants on the outside. Now for these, we're going to use the power rule. Oops. And I'll go get it. There it is. Okay, let's do that. Now, if you notice, when we have this one, the power rule actually applies here too. You can think of this as same thing as this, because x to the 0 is 1. So we're actually using the power rule for all 4 of these cases. So we're going to end up with 5x to the 4th over 4, 7x cubed over 3. We're subtracting that. Don't lose the signs, by the way. 3x squared over 2. Now this one becomes, it's actually 4x to the first over 1, which is the same thing as 4x. And then we always need that constant at the end. So in each case, I took the exponent, and I have now 5, which is a constant, x to the 4th over 4. And I do the same thing for all the terms, and that's my final result. So, so far, so good. I mean, we're doing all the basic cases, and you're learning the basic standard cases that you'll see much of the time. And then, oh, look at this one. So sometimes it might you might be better off like x, the cube root of x, writing it out as x to the 1/3 power to remind yourself. By the way, we have a problem here though. We have a ratio. Ooh, what should we do about that? How about this? What if I divide x into both of these terms? I'll move the 4 to the outside. Now, of course, the quotient rule of exponents tells us this. So there's an implicit one here. So we got the integral of x dx plus 4. So here's 1/3 and x. Okay, now we can apply the power rule to each of those terms. Okay, so x squared over 2 plus c. Now don't forget, don't worry about the c's. We can just put one at the end. And then the integral of this one, I'll move the 4 to the outside. So if I have, here it is. In the numerator, I'll have x to the 1/3 over 1/3, or which is the same thing as multiplying the entire expression by 3. So I have x squared over 2. This one works out to be 12 times x to the 1/3 power. And then we have our constant. Okay, so we basically broke it up into two integrals, and then we applied the power rule to each one individually. So basically, when we're studying integrals, first we have to, of course, formally define them. We want to understand exactly what we're doing here. And by the way, it does relate to limits. But once we've got that done, we're going to focus pretty much all of our attention on learning the different rules. And then we're just going to practice like crazy with all these different integration rules that you might encounter. And we also want to get a talent for recognizing what a problem is or how it's supposed to be solved. And then, if necessary, doing some algebra to take a really messy expression and turn it into something more down to earth. Okay, so now this is the end of chapter 3. So what I'm going to do is stop here, and then the next session will be the review questions from chapter 3. And we'll go through them from start to finish, however long it takes, and then we'll start chapter 4. Okay, so I'll see you all next time.